In question 1, we've got f of x here, a and b are constants, and we are told that when f of x is divided by x minus 1, the remainder is 7, and we need to show that a plus b is 3. Well, using the remainder theorem, we know that if we divide by x minus 1, the remainder is given by f of 1. So f of 1 is equal to 7, which means I can substitute x with 1, leading to 7 being equal to 1 to the power of 4 plus 1 cubed plus 2 times 1 squared plus a times 1 plus b, which leads to 7 is equal to 4 plus a plus b, and therefore we obtain that 3 is a plus b as required. In b, we've got that when f of x is divided by x plus 2, the remainder is negative 8, and we need to find the value of a and the value of b. So similarly with part a, we will say that f of negative 2 is equal to negative 8, which leads to negative 8 is equal to minus 2 to the power of 4, plus negative 2 to the power of 3, plus 2 times negative 2 squared, plus 8 times negative 2 plus b, which leads to minus 8 is equal to 16 minus 2a plus b, and therefore we obtain that 2a minus b is equal to 24, where we have already established from part a that a plus b is equal to 3, and therefore I can add the two equations here to arrive at 3a is equal to 27, and therefore a is 9. Now to find the value of b, I will simply substitute into this equation here, the 3 is equal to a plus b, which leads to 3 is equal to 9 plus b, and therefore we obtain that b is negative 6. In question 2, we've got the first term of a geometric series being 20 and the common ratio being 7 over 8, and we need to determine the value of the sum to infinity. Well, it is given in the formula booklet that the sum to infinity is given by a over 1 minus r, where a is the first term and r is the common ratio. So in our case, the sum to infinity is going to be 20 over 1 minus 7 over 8, which gives an answer of 160. In part B, we are told to find the sum of the first 12 terms correct to one decimal place. Once more, the formula for the sum of the first n terms is given in the formula booklet. In our case, the sum of the first 12 terms is going to be 20 times 1 minus 7 over 8 to the power of 12, all of it over 1 minus the 7 over 8. This gives an answer of 127.7732 ... We need to give our answer correct to 1DP to score both marks, so this is simply 127.8. In part C, we need to find the smallest value of capital N satisfying the given inequality. So starting with what we are told, I will be substituting quantities that I have already found, where the sum to infinity is 160. The sum of the first n terms is given by 20 times 1 minus 7 over 8 to the capital N over 1 minus 7 over 8, and all of this should be less than a half. And then we proceed by observing that the 20 over 1 minus 7 over 8 is simply the sum to infinity, which is 160. So I can write this as 160 minus 160 times 1 minus 7 over 8 to the capital N, close brackets, being less than a half. And then I will collect the numbers on the left hand side. So the 160 minus the half is 159.5, which is less than 160 times 1 minus 7 over 8 to the power of capital N. I will divide both sides by 160, which gives me 319 over 320 being less than 1 minus 7 over 8 to the power of capital N, which takes me to 7 over 8 to the capital N being less than 1 over 320. I will now proceed by taking logs of both sides. So log of 7 over 8 to the capital N is less than log of 1 over 320. And using the power law of logarithms, I can write this as n log of 7 over 8 being less than log of 1 over 320. Now I will divide both sides by log of 7 over 8. However, this is negative, and therefore I need to reverse the inequality direction. So I've got n is greater than log of 1 over 320 over log of 7 over 8. I will plug the right hand side on my calculator. I get that n is greater than 43.198 ... And therefore we conclude that the first integer that satisfies the given inequality is 44. In question 3, we are given y to be the square root of 3 to the x plus x, and we are asked to complete the table below giving y to 3D piece. So what I will do, I'm going to use my calculator to recreate the whole table with all values so I can also check that I've got the right answers. So I press the menu, then 9. My f of x is the expression for y, so 3 to the power of x plus x. I will leave the g of x empty, and I will start at 0. I will end at 1, and I'm stepping every 0.25. So I get the table of values. There it is. The 1.251 is for 0.25. So when x is 0.5, I get 1.494. And when x is 0.75, I get 1.741. In part B, we are asked to use the trapezium rule with all the values of y from the table to obtain an approximation for this integral. So we know that if we are using the trapezium rule, it's always a half times the height of the trapezium, which is the difference between two consecutive values of x. It's the value we've put for step when we were doing the table on the calculator. So it's 0.25, and then it's the first and last y values once, so 1 plus 2, and all intermediate values for y twice, so 1.251 plus 1.494 plus 1.741, and I plug everything on the calculator, giving an answer of 1.4965. In part C, we are asked to explain how we could have used the trapezium rule to obtain a more accurate estimate for the integral, where the obvious answer is to use more trapezium so that we have greater precision, we can follow the curve more accurately, and therefore we've got a more accurate estimate for the given integral. In question 4, we need to prove by exhaustion that n squared plus 2, where n is a natural number, this means a positive integer, is never divisible by 4. So I will split the positive integers into the even and the odds, and I will consider each case separately. We will start by considering n is 2k, where k is in the naturals. This corresponds to the case that n is even. This means that n squared plus 2 is equal to 2k all squared plus 2, which gives me 4k squared plus 2. And we can obviously see that this is 2 more than a multiple of 4, and therefore it is not a multiple of 4. Now we will proceed by considering n is 2k plus 1, where k is in the naturals, so this time we are considering the possibility that n is odd, and we've got n squared plus 2 being equal to 2k plus 1 all squared plus 2, which is 4k squared plus 4k plus 1 plus 2, which can be written as 4 brackets k squared plus k plus 3. This is obviously 3 more than a multiple of 4, therefore it's not a multiple of 4, and therefore we need an overall conclusion that simply says that n squared plus 2 is not a multiple of 4 to complete our proof. Question 5, we've got an arithmetic series, first term a, common difference d. We need to prove the summation formula for the first n terms. So let me start by defining Sn to be the sum of the first n terms, so u1 plus u2 plus u3 plus ... up to un. We know that the first term is a, the second term is a plus d, the third term is a plus 2d, and so on, up to the nth term, which is a plus n minus 1d. And I will rewrite Sn in reverse, so it's the last term, a plus n minus 1d. Then it's the un minus 1, which is a plus n minus 2d plus ... up to the first term, which is a. And I can add the two together, so Sn plus Sn is 2Sn. And we notice that if we pair them up here, we see that each pair is going to be 2a plus n minus 1d. So I'm circling up the pairs. We've got n such pairs, and each pair is giving me the same sum, 2a plus n minus 1d, and therefore the right hand side is n times 2a plus n minus 1d, which can lead to Sn is n over 2a plus n minus 1d, which is exactly what we had to show. Now for this proof to be valid, you need to show the first term, the last term, and at least one intermediate term being added up to justify the conclusion, the final result here. We are then told that the company currently making 200 mobile phones each week will be increasing its production so that they go up by 20 each week. So they've got 200 mobile phones in week 1, moving on to 220 in week 2, 240 in week 3, and so on until they produce 600 in week n, and we need to find the value of capital N. Obviously, we are looking at an arithmetic progression starting at 200, so the first term is 200, and the common difference is 20. We do know that the nth term is given by a plus n minus 1d, and we know that the nth term will be 600. It's going to be 200 plus capital N minus 1 times 20. This leads to 400 is equal to 20n minus 20, and therefore 420 is equal to 20n, which means that n is 21. The company then plans to continue making 600 mobile phones each week, and we need to find the total number of mobile phones that will be made in these first 52 weeks. Now we need to be careful here because we had an arithmetic progression up to the moment we hit the 600 mark, but from that point onwards we continue at 600 per week with no changes, and therefore the total number of mobile phones will be the total number of mobile phones produced over the first 21 weeks, which follows an arithmetic progression, plus the remaining 31 weeks where each week of those will be producing 600 mobile phones. Now S21 is simply n over 2, 2a plus n minus 1d, so 21 minus 1 times the 20 plus the 31 times 600. We plug everything on the calculator and get an answer of 27,000 mobile phones. In question 6i, we need to find the exact value of x satisfying this logarithmic equation. And I will start by collecting the log expressions on the left hand side. So this leads to log of 2x base 2 minus log of 5x plus 4 base 2 is equal to negative 3. Now I can combine the two logs into a single logarithm. We've got subtraction of logs, so this can be written as log of 2x over 5x plus 4 being equal to negative 3. And therefore we have that 2x over 5x plus 4 is equal to 2 to the minus 3. So we've got that 2x over 5x plus 4 is equal to 1 over 8, the 2 to the minus 3. I can cross multiply, leading to 16x being 5x plus 4, and therefore 11x is 4, which means that x is 4 over 11. In II, we need to express y in terms of a, giving our answer in its simplest form, and I will start by writing the left-hand side as log of y base a plus log of 2 cubed base a. I'm using the power law of logarithms here, is equal to 5. So we have log of y base a plus log of 8 base a is equal to 5. Well, we know that the sum of two logarithms can be written as the logarithm of the product. So we've got log of 8y base a is equal to 5, which means that 8y is a to the power of 5, and therefore y is 1 over 8 times a to the power of 5. In question 7, we've got the circle with the equation shown here having center capital C and radius r, and we need to determine the coordinates of C. Now to do that, I will be completing the square, and I will start by writing the x terms together and then the y terms together. So we've got x squared minus 20x plus y squared minus 16y plus 139 is equal to 0. I will complete the square to arrive at x minus 10 all squared minus 10 squared plus y minus 8 squared minus 8 squared plus 139 is equal to 0, which leads to x minus 10 squared plus y minus 8 squared minus 25 is 0, and therefore we have x minus 10 squared plus y minus 8 squared is equal to 25. We can identify the coordinates of the center C as being 10, 8. In part B, we need to show that the radius is 5, and we know that once we've put this in the standard form, then the 25 is the r squared. So we simply say r squared is 25, which means that r is 5, which is exactly what we had to show for part B. We then have that the line with equation x is 13 crosses the circle at points P and Q as shown, and we need to determine the y-coordinates of P and Q. Well, let's recall the equation of the circle that we have obtained in part A. We know that at points P and Q, the x-coordinate is 13. So I will substitute to arrive at 13 minus 10 squared plus y minus 8 squared is 25. This leads to 9 plus y minus 8 squared is equal to 25, and therefore we've got that y minus 8 all squared is 16, which means that y minus 8 is plus minus the square root of 16, which is 4, and therefore we've got that y is 8 plus minus 4, which means that it could be 12 or 4. Looking at the diagram, we see that P is higher above Q, and therefore we conclude that at point P, the y-coordinate is 12, whereas at Q, the y-coordinate is 4. In part D, we have a tangent to the circle from the origin touching the circle at point X, and we need to find in third form the length OX. So going back to our diagram here, remember we've got the coordinates of the center, it's 10, 8. I'm going to draw two tangents from the origin and touching the circle. So the point X could be this point here or this point here. And I'm trying to determine the distance OX. Well, I can draw the radius CX and the distance OC, therefore forming a right angle triangle. We already know that the radius has a length of 5 units, and I can easily determine the distance OC because I've got the coordinates of C. So OC is given by Pythagoras theorem as 10 squared plus 8 squared square root, which gives an answer of 2 root 41, and therefore I can proceed with Pythagoras theorem stating that OX squared plus 5 squared is equal to 2 root 41 squared, which leads to OX squared plus 25 is equal to 164, and therefore OX squared is 139, which simply means that the length of OX turns out to be root of 139. In question 8, we've got two curves, C1 and C2, with the given equations, and we need to verify that the point A over here shown on the diagram has coordinates 1, 1. In other words, we need to verify that this point lies on both the curves. So let's start with C1. I will be substituting x is 1, hoping to get that y is 1. We get that y is 10 times 1 minus 1 squared minus 8, which turns out to be 1. And for C2, when x is 1, we get that y is 1 cubed, which is also 1. And therefore, we conclude that A has coordinates 1, 1. In part B, we need to use algebra to find the coordinates of the point B. Remember, the two curves have these equations shown here, and for a point of intersection, I need to equate the two. So this leads to x cubed is equal to 10x minus x squared minus 8. I will collect everything on the left-hand side to give me x cubed plus x squared minus 10x plus 8 is equal to 0. Well, we already know that x1 is a root because a has coordinates 1, 1, and it's the point of intersection between the two curves. So if x equals to 1 is a root, then x minus 1 is a factor, and therefore I can proceed with the long division because I'm dealing with a cubic, which I don't know how to factorize. So let's start by doing long division. Remember, I'm trying to match the highest order term on the left. So I will start by multiplying by x squared to get x cubed minus x squared, and I deduct, leading to 2x squared minus 10x plus 8, then it's plus 2x, leading to 2x squared minus 2x, again I deduct, and I get minus 8x plus 8, so I need a minus 8 here, so minus 8x plus 8, leaving a remainder of 0 as expected, and therefore we can proceed in saying that the cubic can be factorized into x minus 1, x squared plus 2x minus 8 is equal to 0. This further factorizes into x minus 1, x plus 4, x minus 2 is equal to 0. So we've got either x minus 1 is 0, or x plus 4 is 0, or x minus 2 is 0, which is yielding three different solutions. X is 1, which is obviously point A. X is negative 4, which is rejected since we know that the x coordinate must be 0. And x is 2, which is the x coordinate of point B. So the only thing missing is for me to find the y coordinate of B. So I can simply say that when x is equal to 2, y substituted into x cubed will give me 2 cubed, which is 8, and therefore B has coordinates 2, 8. For part C, we need to determine the area enclosed bounded by C1 and C2. So if I go briefly back to my diagram here, we know that point A has coordinates 1, 1, and point B has coordinates 2, 8. We can clearly see that the parabola is above and the cubic is below, and this is enclosed between A and B. So to find the area R, I will simply be integrating from 1 up to 2. So R will be the integral from 1 up to 2. The curve above was the parabola, so 10x minus x squared minus 8 minus the curve below, which is x cubed with respect to x. So in integration, we are increasing the power by 1, dividing by the new power, which gives me 10x squared over 2 minus x cubed over 3 minus 8x minus x to the power of 4 over 4 from 1 up to 2. Obviously, the 10 with the 2 simplified to give me a 5 here. So if I substitute the upper limit, I will get 5 times 2 squared minus 2 cubed over 3 minus 8 times 2 minus 2 to the 4 over 4. And then I will substitute the lower limit, which will give me 5 times 1 squared minus 1 cubed over 3 minus 8 times 1 minus 1 to the 4 over 4. I plug everything on the calculator carefully, and I get an answer of 11 over 12 squared units for the area R. In 9i, we need to solve for theta between 0 and pi, the given equation giving our answers in terms of pi, so obviously we are in a radian mode. I will start by moving the root 3 cos 3 theta on the right hand side, and I will divide throughout by cos 3 theta to get tan 3 theta. So this leads to tan 3 theta is equal to root 3, and therefore I can find the PV. The PV is shift tan of root 3, which gives an answer of pi over 3, and therefore we have that 3 theta is the PV, pi over 3 plus pi k. Remember, k can be any integer, positive, negative, or 0. I will divide throughout by 3 to get theta is pi over 9 plus pi k over 3, and setting k to be 0 will give me pi over 9, setting k to be 1 will give me 4 pi over 9, and setting k to be 2 will give me 7 pi over 9. We've got a total of 3 solutions between 0 and pi. In II, we've got the given trigonometric equation and we need to find cos x in terms of k. So I will start with what I'm given. It's 4 sine squared x plus cos x is equal to 4 minus k. Well, we know that sine squared plus cos squared is 1. So in the place of sine squared, I'm going to put 1 minus cos squared. So this will give me a quadratic in cos. So let me expand to get 4 minus 4 cos squared x plus cos x is equal to 4 minus k. Collecting everything on the right hand side will give me that 0 is equal to 4 cos squared x minus cos x minus k, and therefore I can proceed with the quadratic formula on cos x. So this means that cos x is minus b, so minus negative 1 plus minus b squared minus 4ac and all square root and over 2a, which is 2 times 4. So this leads to cos x is equal to 1 plus minus the square root of 1 plus 16k and all of it over 8. In part B, we are told that k is 3 and we need to find the values of x in the range of 0 to 360. So I will start by substituting k is 3. This will give me cos x is equal to 1 plus minus 1 plus 16 times 3 square root over 8. This gives answers for cos x of 1 is the first one, or cos x is equal to minus 3 over 4. Now for cos x is 1, I will find the PV, it's the shift cos of 1, which gives an answer of 0. And therefore we have that x is given by plus minus the PV, so plus minus 0 plus 360k. Whereas for cos x being minus 3 over 4, the principal value, the PV, is shift cos of minus 3 over 4, which is 138.590 ... and therefore x is plus minus the PV we just found plus 360k. I can now proceed in generating all solutions between 0 and 360. Obviously here if I put k is 0, I get x is 0, which is a valid solution. It's the only solution coming out from this side. Whereas here, if I put k to be 0, the 138.6 is a valid solution. And if I put k to be 1, I'll do minus 138.590 plus 360, and this will give me 221.4, 3 solutions in total.